All right, so now we're going to talk about the boundary operation and then more generally what are called chain complexes. So previously we introduced this idea of a chain group, right, CPK. So these are sort of the group of formal linear combinations of p simplices with sort of the additive operation, okay, as the group operation. Okay, and if you recall, it's like this is all in service of this notion of homology. Okay, and homology is concerned with the question of finding holes, if you will, or describing holes in some topological space. And as I sort of alluded to previously, right, one of the properties of holes, or one way to sort of describe holes, is in terms of, say, some sort of curve. It's like which encompasses, it's like a hole, for example, right? And so those things are going to be described by curves which are closed, and the property of these closed curves are that their boundary vanishes. Okay, so imagine again, instead of just a one-dimensional curve in two-dimensional space, you imagine, say, the surface of the sphere. It's like again encompassing, say, a hole in the center. In three-dimensional space, again, the boundary of the sphere is empty. Okay, so this naturally, again, it's like so this is sort of suggestive that if you want to describe things like holes of arbitrarily high dimension, one needs to be able to talk about the notion of the boundary. Okay, so first I'm going to talk about this boundary operator. Okay, so so what we're going to do is that since the chain group is just formal linear combination of p simplices, right, we're just going to define the boundary operator first on a single p simplex and then extend it to the entire chain group by linearity. Okay, so we're going to define the boundary operator on a p simplex. Let's call that sigma. Okay, and let's write this as u0 to up. Okay, and extend to the entire sort of p-dimensional chain group by a sort of a linear extension. Okay. All right. So what do I mean by that? Okay. So anyway, so let's see what it means. Okay. So if you take the p-dimensional boundary of sigma, okay, this is just going to be this formal combination from j equals to 0 to p of u0 to uj hat up. Okay, so what I mean by that is that I'm going to omit, so the hat denotes sort of omitting that entry. Okay, so so let me try to be maybe a bit more precise about this. All right, so let's just say I have something like this simplex, all right, which is, let's just call that u0, u1, and u2. Okay, and it's easy to convince yourself that the boundary of that is just this, and this edge, right? So let's call that u0, u1, and u2. Okay, so the boundary of u0, u1, and u2, right, is obtained by saying, let's say u1, u2, right, as a, sorry, u0, u1, right, u1, u2. Actually, I should just add them, right, plus u2, u0. Okay, so this would be the boundary, right? That's quite natural. The boundary of the simplex is just the codimension 1 faces, right? And yeah, so that's actually what's happening here, right? So so in here I've omitted u2, here I've omitted u0, here I've omitted u1, right? So these terms come from, looking through u0, u1, and u2, and then sort of individually deleting one of those vertices. It's like to get some low dimensional simplex. Okay, so that's basically what's happening. So I should say one thing, which is that if you know something about algebraic topology and you're working with the usual integer coefficients, then there's this idea of orientation, right, of the simplex. So there's an ordering, if you will. And then if you were to do that, then there's actually a coefficient here, right, which is either -1 or +1, depending on what j is, in order to ensure that you have a compatible orientation. So normally it's like if you had oriented this simplex in this sort of, clockwise fashion, u0, u1, u2, right, then the boundary would be sort of these edges, but with that kind of orientation coming from the arrows. Okay, so the reason why we don't have a coefficient here is because, again, we're working in Z mod 2Z. It's like coefficients, right? So this is, again, in Z mod 2Z, all right? So in Z mod 2Z, then the plus or minus doesn't matter, right? All that really matters, again, is sort of the set of points. Okay, so that sort of leads to sort of a substantial simplification, if you will. It's like, but it's again important to keep in mind that if you're not working in Z mod 2Z coefficients, there will be a sign here which has to do with sort of the orientation of the simplices. Okay, all right. So in any case, so that's a perfectly reasonable definition in sort of, again, the p-chain group. It's like with Z mod 2Z coefficients. Okay. All right. So some observations, right? So you defined it on a simplex, and then we, as I said, I just extend it by linearity. It's like to the entire chain group, right? So to extend to the entire chain group, right? All I'm basically saying is that the boundary of some linear combination of AI sigma I, right, is equal to the linear combination of the boundaries. Okay, all right. So so this becomes, in some sense, the definition of the boundary acting on a chain is by having that this be true. Okay, so and again, each of these are just boundaries or simplices, and I know how to do that. Okay. So this also has the property that the chain group, the boundary operator, right? You can convince yourself that the boundary operator will map a p chain to a p-1 chain. Okay. Okay. And it again has this sort of property that it's a group homomorphism. So also a group homomorphism, right? Which is to say that the boundary of a sum of chains is equal to the sum of the boundaries of the individual chains. Okay. So again, the addition operation, it's like on the appropriate chain group, right, commutes with the boundary operator. Okay. Yep. Okay, so that puts you in a situation where we can talk about what is called the so this boundary operation is sometimes referred to as the boundary homomorphism, right? So this is sometimes referred to as the boundary homomorphism. or just a boundary map. Okay, and so of course it's like you can sort of string now all these boundary operations together. Right, so you get CP plus 1 maps by the boundary operator to CP to CP minus 1 and so on. All right. And some observations, of course, is that this sequence obviously terminates in some way, because you know that for CP, sort of where sort of P is greater than the dimension of the simplicial complex, right, is trivial. Right, so if there are no sort of simplices of that dimension, then the chain group of the P chain group obviously is trivial. And then C P where again P is less than 0 is also trivial, right? So even though we draw this, it's like there's a sense in which it just ends at C0, and then it ends at, let's say, Cn, right? So there's a finite sort of extent, it's like to this complex, and so this is referred to as the chain complex. Okay. And then oftentimes it's like we just sort of omit the sort of subscript that's like in the boundary operation, right? So often the boundary map. Okay, so we just denote it by boundary instead of boundary sub P, for example. Okay. So, all right, so this gives the idea of a chain complex, and then what we're going to see is that the notion of holes, right, has to do with certain properties or certain spaces associated with the boundary map. Okay, so let me just stop here for a minute.